right, in order for you to be able to simulate what you just saw, you need to be able to compute the equations of motions of photons through space-time. We will start actually with tracing the path of a photon through normal space-time, through Minkowski space-time, which is basically vacuum, the space-time described by vacuum. This is not going to be a primer into differential geometry or general relativity. It's going to be a tutorial on how to obtain these equations of motion, starting from the geodesic equation and the interval equation. So we start with the geodesic equation. It's the following. I hope you should be actually familiar with it. If you are not, then please you can read up on the geodesic equation on Wikipedia or in some textbooks. Next up, we start with the Minkowski metric, which is I choose the signature -1, 1, 1, 1. Of course, we know from special relativity that a photon travels with the speed of light through space. The speed of light is c, and that it can be represented as a curve with the velocity vector, which is the following: gamma dot mu, c mu x, mu y, and mu z. Similarly, we know that the photon is a light-like particle. Like I said, the interval traced through space-time has length to 0, which can be written like this. And this equation actually turns into our speed through the spatial coordinates, mu x squared plus mu y squared plus mu z squared equals with the speed of light squared. So, in other words, our photon travels with c through space. Now let us focus on the geodesic equation. We know in Minkowski space that all Christoffel symbols are 0. And this is because Christoffel symbols are basically functions of derivatives of the metric, given that our metric is only made up of minus 1 and 1s. That means that all the derivatives will be 0. So all the Christoffel symbols will be 0, and that means that our geodesic equation turns into this: gamma double dot k of t equals 0, and this basically means that the light-like geodesic in Minkowski space is a straight line. Now let us look at this straight line in spherical coordinates. So we will start with this scenario. We just have a photon. We pick a center randomly somewhere. We pick it here. And then the orange line is a photon, which starts in this point, travels with velocity c in this direction. And because it travels in a straight line, it will just go up and up and up and up forever. And of course, we now want to describe the motion of this photon in spherical coordinates. If we choose just Cartesian coordinates, it would be very simple, but this is an exercise for us in getting a bit more familiar with the calculations in using tensor equations and so forth. So, and also because spherical coordinates, the metric described by spherical coordinates reference frame, it's actually the metric that we end up if we take the radial coordinate of the Schwarzschild metric to be very, very large. And we will see that there's overlap in how the equations of motion look like. So like I said, this photon moves up and it will always move up. And in our spherical coordinate system, this velocity has two components. We have the radial component, which is r dot t, and the angular component, which is r phi dot, right? So our vector c is split up into these components. We have the radial r dot t r hat plus r phi dot phi hat. All right. Now we start with the metric in spherical coordinates, which is basically this. Of course, I'll add all the references into the video description. And also in spherical coordinates, we notice that our metric is dependent on the angle theta, which is the latitude that we choose to take the motion. And a very good thing about photons in Minkowski space, like we said, it follows a straight path. So that means that it will never leave the plane made by the center of our reference frame and the initial direction. So it will never leave this plane. That means that if we pick the coordinate just right, we have the theta will be constant, and we can just put a value such that our metric is a bit simpler. Now the Christoffel symbols are non-zero in spherical coordinates. These are the only non-zero components. Of course, if we pick theta to be in the equatorial plane, we will get the Christoffel symbols to be this, which is a very simple set. And yes, like I said, one thing that we can notice is that if we take the Schwarzschild metric and take R to be very large, we actually end up with the spherical coordinate system and the metric and the Christoffel symbols, of course. Now, in order to proceed with computing the path using the geodesic equation in spherical coordinates, we replace the top index k with r. So we have gamma double dot r plus the Christoffel symbols r mu nu, gamma dot nu, gamma dot nu. We pick the only non-zero components, and we end up with the equation below, which can be written as such. So this is the first equation of motion, r double dot equals r phi dot squared. Next up, if we pick k equals theta, it's actually, this is just an exercise into doing the geodesic equation, but we don't really need it because, like we said, we picked the equatorial plane, so this is identically 0. Now we can pick k equals pi, pick the only non-zero Christoffel symbols, and we end up with this equation of motion. If we multiply by r squared, we actually notice that r squared phi dot equals a constant, so there is an invariance. This is actually the invariance related to the angular momentum of the photon. So we end up with these two equations of motion, r squared phi dot equals constant, and r double dot r phi dot squared. And using these two equations of motion, we can trace the path of the photon in spherical coordinates. Now, in order to find out what this constant is here in, so phi dot equals constant over r squared, we need to think a little bit of our physical situation. So, like I said, this is the photon, and this is the center of our reference frame. We know that r cos phi equals r. The big R is the distance from the center to the line described by the trajectory, the distance from the center to that line. So r cos phi equals r. We know that the photon also carries angular momentum E equals pc. So we actually end up with, we actually realize that that constant in the equation of motion phi dot equals constant over r squared actually stands for rc. and of course we deduce that by looking at our diagram. Now, in order to proceed, we need to know at least somewhat what Christoffel symbols are, and they basically tell us how to parallelly transport a vector across a path in our manifold. If this is a bit too technical, I suggest to read up a bit on differential geometry basics. But essentially, the idea is that if we start out with a photon that has a certain direction on our manifold, and then we just trace a random path, at the end of that path, that vector generally has another direction, and the Christoffel symbols basically tell us how that direction changes on while we cross that path. All right, so we will start with the convention that our indices are Greek letters, and of course mu will be t, r, theta, and phi, which are the coordinates of the Schwarzschild metric. Uh, Sometimes the Greek letters for mu can stand for, we can write them as basically letters like tr, theta, and phi, or numbers as 0, 1, 2, 3. Okay, of course, like I said, the description, the reference to how these Christoffel symbols are calculated is attached in the description if you want to look for yourself. But based on the Schwarzschild metric that we have, we end up with the following non-zero non-zero Christoffel symbols. As you can notice, we don't have any dependency of our metric on the coordinate phi. That means that this is related to an invariance of the particle trajectory, essentially. And also we don't have any dependence on time, and that also indicates an invariance, which will be useful later on in calculating the equations of motion. Essentially, if we don't have a phi dependency in the metric, that means that our angular momentum is conserved, and if we don't have any t dependency, that means the energy is conserved generally. Okay, now let us look at a light-like geodesic in Schwarzschild spacetime. Of course, start with the metric, and then we can choose, because the angular momentum is conserved, we can actually stick to only one theta, which is basically choosing the latitude plane around the black hole. And once we go for a theta, a certain theta, let's pick the equatorial plane, and our velocity stays within that plane, as in we start with a velocity that it is within the equatorial plane, then that particle will never leave the equatorial plane. In other words, the problem of finding out the trajectory of a particle, of a light-like particle, which is basically a photon, around the black hole reduces to only 2 dimensions, which is fantastic, because solving a problem in 2 dimensions, of course, it's a lot easier than solving it in 3 dimensions. So that happens because what I picked here, it's a non-rotational black hole. And of course, with a rotational black hole, the metric would change. We would have to use the Kerr metric, and we'd have less symmetries to work with. But in our case, the problem of finding out the trajectory of a photon reduces to only 2 dimensions. Okay, so next up we chose the equatorial plane, theta equals pi by 2, and our metric also simplifies. We only have a dependency on the radial coordinate r. Then the space-time interval equation is written here. Um, G mu gamma dot mu equals 0, where gamma is actually the curve described by the photon through space-time. And this is another way to write, of course, the interval equation. Now, if we just, of course, expand out this tensor equation right here, we end up with the following. And if we continue with some further substitutions, of course, the gamma dot t, we can substitute it only using t dot. Gamma dot r would be an r dot. Gamma dot theta would be a theta dot. Gamma dot phi would be a phi dot, as it is here. The theta, it's actually, we picked the equatorial plane, so we're never going to go out of it. That means that gamma dot theta is 0, so we get some simplifications. Next up, we end up here. And of course, like I said, we are looking at the trajectory of a photon, and the trajectory is described by this gamma mu, the curve, of the photon through space-time. Now, the geodesic equation is this one, gamma double dot k of t plus the Christoffel symbol kij and so forth. And of course, this is a tensor equation. Now, if we want to go to obtain the equations of motion, we need to start with some indices, picking some indices, because a tensorial equation contains within itself many equations, not just one. So we pick t, our first coordinate t for k, and we get this equation right here, gamma double dot t plus 2 Christoffel symbols ttr. This is the only Christoffel symbol that is non-zero, which has the upper index equal to t. And we end up with this equation, which if we multiply by this term right here, we actually end up with this final equation, t dot equals a constant over 1 minus rs over r. Of course, this can also be obtained noticing that our metric is invariant with respect to time and using the killing vectors. But again, it's another way to obtain the same equation. It's a rather easier one because we start from the start. We will get actually this equation. But now then, this is the first equation of motion. T dot equals constant over 1 minus rs over r. What we are differentiating with here is the lambda, which is the affine parameter that is describing the path of the parameterized photon curve. Next, we can substitute r for k. We, of course, pick the only non-zero Christoffel symbols that have the upper index to be r. It's these ones right here. Again, the gamma dot theta, it's 0 because we are not going out of the equatorial plane. And we end up with this a little bit longer of an equation. We use the space-time interval equation. We substitute 63. We actually, yes, use 63 and substitute the t dot into 62. And we get this equation, which using some further simplifications, we end up with the second equation of motion, which is r double dot equals r minus 3 over 2 rs, which rs stands for the Schwarzschild metric, phi dot squared. We will see later that this is actually very similar to, it's actually identical. Like I said, if we take r to infinity, we will actually get um, the spherical coordinate system metric in Minkowski space, and what we end up, it's actually r double dot equals r phi dot squared. We will see this a little bit later. So it's extremely similar to the equations of motion described by a photon that is following a straight path in Minkowski space, but we'll see that just a little bit later. Now, of course, we can exchange theta for k to find out the um, equation for motion for theta, but like we said, we are in the equatorial plane, so we ignore this, and then k, we substitute k for phi. We pick the only non-zero Christoffel symbol, and we end up with this equation of motion right here. And of course, we notice this is identical to the Minkowski space in spherical coordinates with the equations of motion in Minkowski space. So now we end up with the following equations of motion. T dot equals constant over the following term. R double dot equals R minus 3 over 2 RS phi dot squared. And phi dot equals another constant over R squared. But as we saw in the example of a photon going along a straight line in vacuum, the second equation of motion, R double dot, the first term in this equation is actually identical to a photon just going in a vacuum, and we have a second term that makes all the difference for, of course, the Schwarzschild metric. And we actually realize that the phi dot squared, the constant in the phi dot equation, is actually RC, as we saw in example, uh, the example that we had previously in vacuum. And this is because if you take R to be very large, we know from the vacuum solution that this constant is RC. So if the photon started very far and it had that um, parameter, basically the impact parameter, then it will stay the same no matter how close it gets to the black hole. So we found the value for this constant. Okay, then now we can focus on the initial conditions, because now we know the equations of motion, but what we're missing is just the initial velocity of this photon. Otherwise, we can set the initial position wherever we want, but as we will see, the actual initial velocity has to um, respect a certain law. So let's look at the velocity of this photon that is following a geodesic. We have the interval equation as we wrote it above, which is this. We use the equation of motion for the time coordinate, and we replace this t dot in the interval equation. We get the following, and finally, just by doing some rewriting, we end up with this equation right here, number 80. And we notice that if we pick an r, then we end up with an equation which looks like this: r dot squared on a constant squared, r dot squared over a constant squared, and phi dot squared over a constant squared. which is actually the equation of an ellipsoid. So if we wanted, for instance, to specify all the directions that a geodesic can take from a point, as in all the directions, right, of that photon, then the shape described by the tips of all those velocity vectors will actually end up on an ellipsoid, not on a circle. And this is because space, as we see, space-time is actually bent by the mass of the black hole. So instead of a circle, we end up with an ellipsoid. And now thus, if we pick a direction, we um, parameterize that direction by an angle psi, which can take any value from 0 to 2 pi. And this is basically our initial velocity now. R dot equals C cos psi, and phi dot equals the following. So now we know the initial velocity, we know we can set whatever initial position we want, and to develop the trajectory of the photon, we just use the equation of motion. So everything is finally solved. Okay, another important step in actually performing our simulation is what is called ray tracing. Again, I'm not going to give a primer into um, or I'm not going to go into very many details on what ray tracing is, but basically it's a technology that is used by mostly all video games these days, and the basic concept is that we imagine a camera in in our in our video game, in our simulation, and for each pixel of the camera we of course get the center of that pixel, and we imagine rays coming out of each pixel. So we take the camera center, we have the pixel center, and then we simulate the trajectory of a photon that takes this essentially this trajectory. So it started out in the camera center, it ended up in this pixel, and then it follows that trajectory through space. If it collides with a green object, then this pixel will be green. If it collides with a reflective object, then the ray will maybe collide with another object later, and so on and so forth. And looking at what this ray collides with, then we can infer what the color of this object is, how bright it is, and so on. But essentially, this is what I had to do also for my simulation. I had to simulate a viewport in 3D space, take a bundle of rays that have a direction. Each single ray is associated with one individual pixel, and then I just use the equations of motion to figure out where they actually end up. And the final step of our ray tracing algorithm is, like I mentioned before, our 3D static black hole problem is actually reducible to only 2 dimensions. So we first of all take the initial direction of that ray, and then we rotate the ray, or we rotate our coordinate system such that ray falls into the equatorial plane. Then we end up with 2D um, equations of motion problem. So we already computed the equations of motion. We know the initial direction. So we just look what the trajectory of this photon will be. So, for instance, this ray that I just took now, it starts off here, the trajectory bends, and then it ends up somewhere on the boundary. I took, for instance, in my simulation, I took the boundary to be 50 Schwarzschild radii. Um, I could have taken it to 100, that doesn't matter too much. At 50 Schwarzschild radii away, the trajectory doesn't bend that much. So I just assumed that whatever direction this photon will have at 50 Schwarzschild radii, it will keep on going exactly in that direction up to infinity. And then the very last step is, because now I started with my initial photon, right? With the initial direction, I know the end, the final direction. Now I just need to map that final direction onto onto an image. So in this case, this would be the image of the background sky, or the image of an infinitely big cube, which are the two options that I showed right here. So essentially, I need to map each and every so these directions, right? These directions described by the rays end up on a sphere. I can imagine a sphere, and I can assign a latitude angle and a longitude angle for that direction, and I need to map that theta and phi, that latitude and longitude, onto an image. And luckily we have what is called an equi-rectangular projection image, which gives me, for every single pixel of that image, is actually associated with a latitude and a longitude angle. So I can use an equi-rectangular projection image so that I can basically build my image, my 3D image. Now I'll show you what the equations of motion actually result in. I made a 2D black hole simulation and also a 3D black hole simulation, but we start with a 2D black hole simulation because, like I said, we can trace out the trajectory of a photon in 2 dimensions. Uh, and this is a simplification that is a result of the metric not being dependent on uh, phi, on the angle phi. Let's look again at the equations of motion. The equations of motion are the following here. R double dot equals R minus 3 over 2 RS, and phi dot equals constant. What I'm interested in now is the 3 over 2 RS. So this actually, as we can see from the equation of motion, once we get to radial coordinate that is lower than 1.5 Schwarzschild radius, then our acceleration with respect to the radial component becomes negative. So that means that within this 3 over 2 RS radius, we cannot have any um, any orbit that is stable. And the way that this actually pans out in the simulation is, so when I press click, um, I create photons going in all directions, and as you can see, the initial velocities follow more of an ellipsoid rather than a circle. Because, like we already talked before, the initial velocities of geodesics end up on an ellipsoid. So now, if we look within this gray circle, this gray circle actually defines the border of of our 1.5 RS region, which is actually called the photon sphere. So any photons that start within the photon sphere, if they would try to orbit the black hole, they would actually end up inside of it. So no photons survive. If their initial direction is straight outside, they still can escape. But if they are on a trajectory that in an otherwise Newtonian space, they would orbit. Here, they just get absorbed, as you can see. At this coordinate, if we are outside of it, uh, there are there is the possibility of actually orbiting if we were along the spaceship, for instance. All right. Okay, so this is the simulation of the black hole in 3D space. Um, and what I'm seeing here is the black hole, of course, the distortion created by the Schwarzschild metric. And all around me, I have the night sky. So this is actually an image of the Milky Way. So up and down, there's not much to see. However, in the galaxy plane, I have a lot more detail. So what I'm seeing in this simulation is basically this is called the Einstein ring, and essentially what it is if I'm taking a photon that initially it goes into the direction of where my pointer points at. If it was vacuum, it will just go straight into that direction as we discussed. If if the metric it's a Schwarzschild metric, it will actually bend. So the trajectory will start out like this, and it will be bent by the black hole gravity. So it will end up in a different direction. So the photons that start out in this direction will bend less, 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 and they will bend less here, a little bit more here, a little bit more here, more, up until at this point, actually these photons bend such that they become parallel to the direction described by the camera center, which is basically your eye, and the center of the black hole. So they will bend a little bit more, up until they become parallel with the direction described by just looking straight into the black hole. And this means that all those photons will point into the exactly same direction, right? Because they are parallel with my direct line of sight to the center of the black hole. So they will point essentially to the same point at infinity. And so they have the same color. So that's basically what happens here. This circle, well, which is called the Einstein ring, it actually describes exactly that. And then, like I said, so the trajectory bends more and more as you go in, and when you actually go inside that Einstein ring, you actually find that the direction is reversed. Now, for instance, we can see very well if we go a little bit later into the orbit. Let me see where it is, because there is also a galaxy. All right, it's here. Okay, and we need to orbit a little bit more. All right, we get closer to the galaxy. All right, so now, if the black hole wasn't there and I would look down, that would be the galaxy that I'm looking at. But now, if I'm looking inside the Einstein ring, I'm seeing the galaxy, a reflection of the galaxy here, because the photon that is going from that galaxy is passing behind the black hole, and then because it's bent, it's actually bent so much that it ends up in my in my view, in my camera, essentially. So I'm seeing a reflection of it right here. We can go even closer, and we can also orbit while we are at it. And here, within this Einstein ring, I also have my photon sphere. So essentially now I am approaching the photon sphere. And the photon sphere, we will reach it when the photons that go, they try to go tangentially to the black hole, will actually end up inside the black hole. So we get closer, closer, closer. Now we get very close to the photon sphere. Very close, very close, very close. At some point, the black hole surface in our view will become straight. All right, so now we are inside the photon sphere as well. Because if I'm looking away, I'm trying to look away from the black hole, right? So this would be a perfect perfect tangential direction. But as we can see, I'm looking in this direction and the photon is actually falling into the black hole. So we are now definitely in the photon sphere. And this is the Einstein ring seen from inside the photon sphere. So now we go even closer to the black hole, closer, 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 up until all directions become null, apart from a very definite cone that is opposite to the center of the black hole. So now I'm very close. I'm exactly on the edge of the event horizon. And I can change my orbit angle. And now essentially I'm seeing the whole panorama of the sky in just one direction. And now I can start orbiting this black hole. It would look something like this. What I can also do to explain the way that the black hole bends light is to look at a similar problem, but looking from inside of an infinitely big cube. From looking inside of an infinitely big cube. So this would be the cube. This is the way that the infinitely big cube would look if I would be very close to the event horizon. Of course, if I go very far away from the black hole, the cube looks normal. It's a normal looking cube. And this is the black hole. I will align the orbit such that I go in the middle of the cube. All right, and then all right, now it's the middle of the blue face, this cube. And I can start orbiting. So this would be the way that a black hole inside of an infinitely big cube would look like. As we can see, some of the rays here actually are bent such that they end up into the blue face of the cube. The rays here are bent such that they end up into the top face of the cube, which is white. these ones end up into the bottom, which is yellow, and so on and so on. And this, of course, this ring, it's the Einstein